So partial derivatives are one of these things that when I didn't know what it was, like when I was still maybe in early calc, I would hear, or maybe not even, I would hear like I knew what a derivative was, but I didn't like the word partial derivative. It just sounded so cool to me. Like people would be like, "Oh, I I I computed the partial derivative for the wave function." I don't know. Like I just thought that sounded so cool and so nerdy, and I was really excited to learn. And here we are talking about partial derivatives. So in the 2D world, um, the, the concept of a derivative is that, hey, I want to see how does my function change, right? Calculus is all about change. How does my function change? And, as I go along the x-axis, does my y value, does it go up? Does it increase, decrease? And how quickly does it change? That's the concept of a derivative. It looks at, hey, um, this itself isn't really a derivative. This is just saying, hey, for some dx, for some change in x, that's really all what dx means. For some change in x, what is my change in y? And then when you take the limit as, I guess, dx approaches 0, right? As dx becomes smaller and smaller and smaller, dy would become smaller, but eventually you would get the derivative. And the derivative, right, would look like the tangent line. So if I were to take dx, or if I were to take the derivative at this point, I would essentially get the tangent line. And this tells me, hey, how does my function grow at that point? The thing about the 3D world is that think about, like, if you think about I forgot to label these. If you think about how does my z value change? Well, the deal is there's a lot of okay, in the 2D world, it was like, how does my dy change? Well, it changes according, depending on x, like depending on my dx, right? There's only one path, right? As my x increases, what happens to my y? That was very simple. Maybe computing a derivative itself is kind of hard, but at least the idea is like, how does dy change, or what is my dy over dx, right? That, it's only one way. You just increase your x value and see how does your y value change. But in the 3D world, the problem's a lot bigger. If I'm thinking about, hey, how does my z value change at this point? Well, it depends. Does it change, like, does it change, like, do you want to see it changing going this way or this way or this way or this way? There's so many paths that your z value can change. And, in that sense, how do you take the derivative? Well, there is something called the directional derivative, and that'll tell you how does your z value change for any path. But to construct that, we first need to understand the partial derivative, which says, hey, I drew these circles, right? Like this circle represents like cross sections of like y, so y equals 0, y equals 2, whatever. And then I have cross sections for the x-axis, right? When x equals 1, x equals 0, so on. How does my z value change as I change my y? And how does my z value change as I change my x? That is the idea of a partial derivative. It's saying, hey, how does my z value change when only one variable changes? You can see along this circle, this is all on the same y, right? This is like a cross section between, or this is like I guess like the cross section between the intersection of a y plane and this dome, this circle. This is just x squared plus y squared plus z squared equals 9, where z is greater than 0, and then you can solve for z, and you get an actual function. How does my z value change as my y value changes? And I just now realized these aren't circles. They should be half circles. Point is this isn't looking at how does my y value change. It's looking at how does my x value change, and how does that impact z. So the way we write this is, if I want to see how does z change with respect to x, right? I'm not changing the y. I'm just seeing how does changing x change z. I can say this notation. So partial z, partial x, or partial f, partial x. So instead of using these, we use partial. The partial symbol. I think this is some Greek letter, I'm sure. Or maybe it's not. Maybe it's just that word. Or it's just a symbol we came up with. Partial z, partial x, same idea. Well, how does my change in z compare to the change in x? It's kind of like that ratio. And then obviously you're taking those changes and making them really, really small to get the actual partial derivative. And obviously for y, it would, kind of be partial z, partial y, or partial f, partial y. So another notation would be something like f of x, and f of y. And then for second derivatives are a little bit crazier because here's the deal. Let's say it's a little hard with the sphere to kind of show you what I'm talking about. Let's just do it. Okay, so your derivative in your partial f or partial z, partial x, or whatever, I could have said partial f. Your derivative, right, can change. That's the idea of a second derivative, is how does your derivative change? Well, your partial z, partial x, your partial derivative for the x direction can change by moving along the x value, or x-axis, and the y-axis, right? Because you could see, if I have my partial derivative, so for example, the most intuitive is like, okay, how does my partial derivative for x change with respect to f? Well, that would be like, okay, as I move along the x-axis, so I'm moving along the x-axis already, but then how does my slope change? And by the way, the partial derivative would look like the tangent line for that sort of cross section. So how does that change as I move along the x-axis? But also, how would my partial derivative for the what's the word? Why am I not getting the word right? I should get the word right. Let me look at my book. What did they say? With respect to. So how does the partial derivative with respect to x change as I move along the y-axis, right? Because my partial derivative in the case of a sphere, I think in the case of a sphere it would be different. As I move along the sphere in the y direction, how does my partial derivative for the x variable stay the same or change? That is oh my god, what's the word? It's the second partial derivative with respect to x with respect to y? Yeah. Hopefully that makes sense. And you could do the same thing for y, right? F of y, or f of yx. So let's just go ahead and compute. How do you compute a derivative or a partial derivative? Well, let's take the case of a sphere. To compute this, what I'm going to do, so let's say I want to find first partial z, partial x. Because my y variable is not changing, right? Because I'm taking this kind of intersection of two surfaces and using the cross section, the y, when I'm taking with respect to x, the y variable becomes a constant. Because you can see everywhere along this cross section, the y is a constant. So I would treat it like a constant, like it's like a number almost, right? The same way I would treat 9. So to take this, and all your derivative rules apply. That's an awesome thing, because at the end of the day, a partial derivative is really just finding the derivative of kind of that curve, right? And finding, finding the derivative of a curve. So your regular Calc 1 derivative rules work great. I would do chain rule here, so I would say so the derivative of 1 over root x the derivative of root x is 1 over 2 root x, and I can derive that, but I just have that memorized. So I would keep everything inside for this, and then I would multiply by the derivative on the inside. The derivative of the inside part, that's a constant, don't worry about it. For this, it would be negative 2x, and then for y, that's a constant. So partial, if I think about partial y, partial x, I guess, if we're doing the chain rule like that, partial y is 0, because my y value is not changing, right? It's a cross section, so that becomes 0. So partial z, partial x, or fx, is going to equal negative x over root 9 minus x squared minus c squared. And if you're clever, you could say, hey, well, root 9 minus x squared minus c squared, that's also just z, right? Like, my z value is defined by this square root in the bottom. So it's also negative x over z, which should make sense if you've ever taken the derivative of a circle before. But I'm just gonna leave it in terms of y's and x's. And then I can also take, and then I can also do f of y, which is going to equal, okay, this is going to equal, so I'm going to do, why am I blanking on this? I have to look up. I was looking at this, I was like, wait, what? And I was like, oh, I have to go back here. Because, right, I'm taking the derivative of the same function just with respect to another variable. So you can imagine it's going to be very similar. Because really now it's just, I'm taking the derivative with respect to y, so the x becomes a constant. So I get 1 over 2 root 9 minus x squared minus y squared times derivative of the inside would just be negative 2y. So I would get negative y over root 9 minus x squared minus y squared. Let's just take some second derivatives now. If I were to take the second derivative, f of x, right? I guess it would be the second derivative, the second partial derivative of z with respect to x. This is f of double x, I guess. So this you would use your quotient rule in this case. So I would say, okay, low d high, so low 9 minus x squared minus y squared, low d high. Oh, this is going to get kind of crazy, okay? This actually might get really nasty, but we're going to do it. Times the derivative of the top, negative, minus high, so I'm actually going to get plus x, d low, so 1, I would actually just get negative x over root 9 minus x squared minus y squared. Because then when I take the derivative of this, I just get back to this. You know what I mean? Over 9 minus x squared minus y squared. So f of double x is going to equal, you essentially get, okay, this is kind of crazy. Because you can actually algebraically manipulate this. I can factor out a negative, and I get, I'm gonna let this just equal z really quickly, and then I'll substitute things back in, because these are all z's. So I get negative z, and I can factor out that z, and then I get plus x squared over z, right? Because I have a z on the bottom here. And I factored out a negative over z squared. And then that just becomes, then I can make this z squared over z. So then I get z squared plus x squared over z squared, the whole thing over, and that would leave me with negative z squared plus x squared over z to the cube. And then I could substitute things back in, but I'm not going to do that. And please check my work. I could be wrong. This should be in parentheses, but this could be wrong, because I'm freestyling this. I didn't do this example. You can do the same thing for f of x, y. I'm going to really quickly do f of y. I'm going to do f of y x, because there's a theorem. It's called the Clairaut's theorem. Clairaut's theorem. I think that's how you say it. This theorem actually tells us that f of x, y is equal to f of y x in most cases. This is the actual theorem. Suppose f is defined on a disk D that contains a point AB. If f of x, y and f of y x are both continuous on D, then they would be equal. They would both be equal. I don't know where he's getting disk from, and to be honest, I don't fully understand this theorem yet, but I'm going to try to. We're just going to roll with it and just hope it's true. You can always just manually do it and show that they're both equal. But I'm just going to take f of y x right here. So for f of y x, I would say, hey, right, so f of y x, okay, I shouldn't say it like that. How do I say this? I don't know. They don't really give a verbal, thing. Let's just find this partial derivative. Fine. Well, that's just what I'm going to say. So I would use quotient rule again. So I would get this 9 minus x squared minus y squared. And then I would do the kind of same thing. I would get this minus negative y for the high times the derivative of the lower. So this would just become negative y over x squared. Oh, I forgot the negative here. Whoops. Okay. Negative y over root 9 minus x squared minus y squared all over 9 minus x squared minus y squared. This is all just low d high minus high d low over low squared. And then I can substitute this in for z. So I can say, I can factor out a negative once again. I get negative z plus y squared over z squared, negative z squared, and I just get negative z squared over y squared over z cubed. And you can imagine if you were to do this, if you were to take f of xy, it would indeed be the same. So key idea for partial derivatives, treat it like a constant. One thing I want why did I say that so quickly? Why did I rush that? Key idea for partial derivatives, if you're taking the partial derivative with respect to another variable, so with respect to a variable x, the other variable y can be treated like a constant. That's kind of the main idea, and this should kind of explain why, right? Because when you're taking a partial derivative, all you're really doing is taking the derivative of the curve of the cross section of, oh my god, of the surface and the y plane or the x plane. So, or like the yz plane, xz plane. So, really quickly, what I want to talk about is using level curves to kind of get an idea about the partial derivatives at play. So, for example, let's just say, should I use one from the book? What's a good one from the book? Is there any good ones from the book? Okay, let's just use this example. So let's say I have level curves, and the level curves kind of look like this. Okay, these are the level curves. I hope they're not too faint. And we could just say 10, 8, 6, 4, 2. And I want to say, okay, this is point P right here. What are the signs? Okay, what are the signs for f of x, f of y, f of xx, f of, okay, I should not say f of x. That's just not good math. Partial derivative with respect to x, partial derivative with respect to y, second partial derivative with respect to x, second partial derivative with respect to y, and then the partial derivative of x differentiated with respect to y. Sure, fine. I will work. Here's a little secret. I'm actually learning Calc 3 for the first time. I don't make these videos until I fully understand the concept, but that's why I sometimes don't know these small little things. But we're going to roll with it. So I want to find the signs, right? Whether it's positive or negative, each of these values. And these are the level curves for the function. So for f of x, I want to look at, hey, as I move along the x direction, so as I move along the x direction, along this dashed line, what is happening to my function? Well, it starts at a value 6, and it's going from 4 to 2. So I know my z values are decreasing as I go from point P along the x-axis. So the partial derivative with respect to x would be negative, right? The function is simply decreasing. For f of y, I would do the same thing, but now in the y direction. So as I go up the y direction, I can see, hey, my function's increasing. I start at 6, and then I go to 8 and 10. So I know this is increasing. For the second partial derivative with respect to x, I'm looking at, now how does my derivative change? And to get an idea of how my derivative changes, I need to look at the spacing, because I know that greater spacing means a greater, right, let's just use this, right? Partial z, partial x, right? More spacing means this is bigger, right? Like, if I increase the spacing, that means a greater partial x, greater change in x for the same change in z. So that would be a smaller derivative, right? A smaller partial derivative with respect to x. So as I go along the x-axis, this is like my z values change less and less. The spacing gets bigger, so that just means that greater change in x for the same change in z. The derivative is getting smaller. So if my derivative is already negative and it's kind of getting less and less in magnitude, my second derivative must be positive. Because the partial derivative is negative, and then it's getting less and less negative. It's getting more towards 0. So the second partial derivative would be positive. I can do the same thinking here. I see that the spacing is getting smaller, so the partial derivative with respect to y is getting larger. So because it's already positive, that must mean f of y is positive, right? This is kind of like Calc 1 stuff, thinking about, okay, if my derivative, if I think about right here, right here, it's positive and it's concave down, so I know the second derivative must be negative because the positive derivative is getting less and less positive. It's that sort of thinking. And for f of xy, this is where you really got to think, right? This is where you kind of have to think. This is saying, hey, as I move along the x-axis, let's think about it like this. Let's say this arrow represents the change in the function with respect to x. Then as I move along, does this arrow, right, does the change in z get larger or bigger with respect to the x, okay? So I guess I shouldn't use the arrows. I don't want to make this a vector thing. This is just to visualize. I can see here that, oh, this gap between 8 and 6 is smaller, so it's a greater derivative, and a greater partial derivative with respect to x. Same thing as you go up to 10. So the derivative is getting bigger, but the derivative is still negative, right? I'm still going from 10 to 8. I'm still going from 8 to 6. So it's getting more negative. So f of xy would then be negative. Did I do this right? I don't think this is right. Let me check the answer key. I think I messed this up. And if I did, I want to see why I messed it up so you don't make the same mistake. But I did this exact problem though. And I got it right the first time. Oh! No, I'm right. I just messed up. I did the order differently, so my answer looks different. Yeah, this is good. This makes sense. Okay, perfect. So yeah, this has been partial derivatives. Not a crazy concept if you're good with derivatives already. So hopefully this wasn't terrible or anything. But yeah, thank you for watching.